Classifying numbers. So this is the first note sheet in this unit. Um, so basically we are reviewing all the number systems and classifying numbers in the real number system. So let's take a look at the first part. When was the first time you heard about numbers? You probably learned to count from 1 to 10 at a very early age, but since then you have encountered a variety of different types of numbers. List some examples of all the different types of numbers you have seen. Search your memory hard for some of the more obscure ones. So I'm sure you've seen, well, I know you've dealt a lot with integers, fractions, that kind of thing. You've talked about numbers like pi. Pi is an irrational number. Maybe you've heard about, so that's a little bit different one, obviously, fractions, integers, fractions, decimals, repeating decimals. This is irrational. You may have heard of a number e. That's also irrational. You will learn about that in grade 12 math. Yeah, so those maybe are some of the different ones that you can you've seen. Now, actually, speaking of irrational, square roots too. So square root of 5, for example. Square root of 4 is equal to 2, so that is not irrational. These three are irrational. These are all rational, and that's what we're going to get into in this lesson. So math groups numbers into various types. Here's how mathematicians classify numbers. So you'll notice some notations here. So these are your natural numbers in Alberta education. Actually, I'm going to switch this to blue. Alberta education and Canadian education, we use N for natural numbers, okay? So when you write the diploma exam in your grade 12 course, that's the notation that we'll use. IB uses this notation, so this is IB. Okay, so why is that Z? Well, if you look down here in IB notation, which is more, this comes from other parts of the world, and namely Europe, I think uses Z for integers. So if Z is for all integers, natural numbers are all the positive ones. So that's why they put a little plus there. Okay, so just be aware. Whole numbers are naturals with a 0 in it, and if you think about, I always think about how I remember this. 0 has a hole in it, not spelling, but an actual hole in the center, and so that's how I remember that they are whole numbers. Kind of a little trick. So in Alberta education, makes sense. It's a W, so N for naturals, W for whole numbers, I for integers. But now IB, they use N for whole numbers, and probably again it comes from a different language or something. Maybe N is the first letter. In any case, you do need to remember that. Integers in Alberta, integers in IB curriculum. Okay, so integers have all the whole numbers and now all the negative natural numbers. Okay, rational numbers is Q, no matter what. Probably comes from the word quotient, is the answer when you divide. So Q for rational in both Alberta and IB curriculum, and that's the set of all numbers that can be expressed as a fraction, where A and B are integers and the denominator is non-zero. So rationals include all of these. Okay, it's includes all fractions like 2/3, -17/4 that don't reduce, but you can show For example, here, -5/1 is -5. That's a fraction made up of integer, numerator and denominator, and we get an integer answer. So integers are part of rational numbers. Sometimes you will see Q with a plus. That's the set of positive rational numbers. You don't end up seeing that very often. Then irrational numbers, no matter which Alberta or IB, is Q with a bar over top. Sometimes I have seen it with Q with a prime symbol, but for what we're doing, it's Q with a bar. Okay, so that's the set of all numbers that cannot be expressed as a fraction, where A and B are integers and the denominator B is not 0. Okay, so you can't end up with showing it as a fraction, and that really means they are non-repeating or non-terminating decimals when you show them as a decimal. Okay, so that can't see a pattern that repeats. Root 12, 12 is not a perfect square, so that's not going to be able to be simplified. Pi we already talked about. Cos of 30 degrees, that's a trig that we're going to learn this unit, and really that can be expressed as a fraction where one of the components, the denominator, is a irrational number. Okay, so that's how we know that the whole thing is. And real numbers are, again, same for Alberta and for IB, that is all of the above. Basically, it's a union of the sets of rational and irrational numbers. Okay, the odd time you might see R plus, that's a positive real numbers. Okay, so let's do some work here. So note that all of the natural numbers are in the set of whole numbers, and all of the whole numbers are in the set of integers. For example, the number 4 is not only a natural number, but also a whole number and an integer. We say that the natural numbers is a subset of the whole numbers, which in turn is a subset of the integers. We can represent the relationship between the natural numbers and the whole numbers in the diagram below. Add to the diagram the set of integers. Okay, so here is your natural numbers. So these are your whole numbers. These are your natural. And so actually I can do a box here, I think. Oh, that was a circle. I guess I have to choose this. I'll erase that in a sec. So there is a box. Okay, and so that is the set of integers. So remember for IB, it's a Z. And you'll notice back up here how they are bolded. So when they're bolded, kind of hard to do bolding. You'll notice these aren't. You'll see I often do a double line, okay, which kind of makes it look bolded. So it's always, so for N, I do a double line for the first vertical. For Z, I do a double line like that. That just means the set of integers, okay? So these are integers here. All right, so that is, we've added the set of integers. Okay, we're going to come back to this in a sec. Let's go to the next part. The number 4 is not only a natural number, but also a whole number and an integer. Is the number 4 also a rational number? That is, can 4 be expressed as a fraction? If so, how? So yes, it can. So you can show 4/1, or you could show 8/2, or you could show 16/4, etc. Okay, there's many different ways of getting 4. I've just given you, you could do 100/25. Okay, it doesn't have to be a multiple of 2. So, yep, that confirms that it is a whole number, that it is a rational. We already knew that it's a natural number, whole number, and integer. Can every integer be expressed as a fraction? Yes, it can, because you can always remember the definition for that rational. These both have to be integers. So if our denominator, if we're trying to express an integer as a fraction, we can put it in the numerator and just put 1 in the denominator. Okay, so yes. Okay, is the set of integers a subset of the rational numbers? That is every integer also a rational number? Well, we just said yes here, so yes it is. Okay, based on the above. So go back to your diagram in question 1 and add the set of rational numbers. Okay, so I'm going to go back and then try to do a better job of this. Here. And there we go. It's going to be our rationals. Actually, I'm just going to move that a little bit like that. Is that? Okay, so that's Q, and so then I put a line on the left. Okay, so that's rational. All of these are part of the set of rational numbers. So we've done that. Okay, so rational numbers were described as fractions, but they can also be described in decimal form, since all fractions can be changed to decimals. How is this done? So for example, 3/4. Remember how you probably know that, or you should know that that's 0.75. Okay, how do you get that? You divide. So you take the numerator and divide by the denominator. Okay. Convert the following fractions to decimals. So hopefully you know some of them. 2/3. Remember, 1/3 is 0.3 repeating. So 2/3 is double that, 0.6 repeating. Okay. 1/9. Anything with a denominator of 9 is going to basically be a multiple of 1 repeating. So if this is just a 1 here, it's going to be 0.1 repeating. If it was 2/9, it would be 0.2 repeating, etc. Okay, this one might not know. I don't know it off the top of my head. So in your graphing calculator, or any calculator, don't really need a graphing for this. I'm just going to do the 7/11. Okay, so 7 divided by 11, and look for a pattern. So if there is one, but it should be, we know, because this is a fraction made up of integers, so it should either repeat or terminate. Okay, and it's pretty obvious here. So 0.63, 63, 63, 63. Notice how at the end it's 64. That's because the next digit, it really should be 636, and the calculator has rounded that up to a 4. Okay, so this is 3 plus 7/11. So you could actually, if you want to, just add 3 there. And so it's going to be 3.63 with a bar over the 63. Okay, so these are repeating decimals. Convert the following fractions to decimals. Again, same thing as above. So if you're not sure, like in my head, what I do here, try to use some mental math. 4 goes into 17 4 times, with 1 remainder, so that's 4 1/4. So that's 4.25. Okay. 3/16. Maybe you don't know that off. Sometimes I have to check that one personally myself. So 3 divided by 16, right, 0.1875. This one will be 2 decimal. And then remember 3/5. I always think of, oh, okay, well, that's easy to get a denominator of 10. That would be 6/10. So that's 2.6. Notice how none of these repeated. They're all terminating decimals. So how do these differ from those above? These are terminating decimals. Okay, in summary, when a fraction is changed to a decimal, the decimal either repeats or terminates. Use your patterning skills to determine the 50th digit of the decimal expansion of 1 over 13. So this should be a bit of a review. Not that you have to do this very often, but let's figure out what 1 divided by 13 is. Okay, so 1 divided by 13, 0.076923, and then I see a 0769. So these are all repeating, even the 0, okay? So let's think about how many digits are there here. So there's 6 digits, and we want to find the 50th digit. So if you think about, we've got 6 digits and then another 6 digits. So basically, how many 6s go into 50 without going over? Okay, well, 8 times 6 is 48. Okay, so really what we're doing here, just expand this out, is 50 divided by the 6 repeating digits. 8 goes into that with a remainder of 2. So that means basically here we'll get to 6, and there will have been 8 of these, and then we'll have 2 digits of the next set of repeats. So we have to look for the second digit, and that's a 7. Okay, so this would be 0, 7. So use your patterning skill. So the 50th digit is 7. Okay, let's take a look at the next part. Question 5, the following are examples of irrational numbers. Use a calculator to express the last two in decimal form. So you can see there is a pattern, but it's not repeating. And we have dot, 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 so we don't know what comes. We're assuming, like, we can't assume anything because there's no pattern to know what's going to repeat. So we have to assume that it's not repeating. And then root 12. Let's get our calculator. Root 12 is, let's see, it doesn't say how many decimal places, so 3.464101615, etc. So although you might see some ones there, there's no repeat to it. And pi, remember, use the pi button in your calculator. Some of you will know a few digits of pi. So 3.1415926554, etc. Still haven't found all the digits of pi. If you ever meet Mr. Yanover, math teacher at Wisewood, or have him as a teacher, he can recite them really fast, like he knows a couple hundred of the digits off by the top of his head. So ask him about it. How do these decimals differ from those in question 3D? They neither terminate. Oh, sorry, 3D. I better just check what 3D is. 3D. There isn't a 3D. I think it was 4D. So they do not repeat or terminate. So can a number be both rational and irrational? No, because these are basically all the decimals that do not repeat or terminate. So it kind of fills in all those empty spaces. So go back to your diagram and add the irrational numbers to your diagram. Okay, so irrational, oops, page 4, Irrational will be entirely separate. So I can basically do a box here. Oh, sorry, I had to just span this out. There we go. Okay, move it up a little bit. Close enough. Okay, so this is irrational. So that's Q. Oh, Q with a bar. Sometimes it is a prime, but we'll use a bar, and that's irrational. Okay, so it's separate from rational. Rational and irrational, and all of these together, this whole thing, is the real number system. All the real numbers. Okay, so let's go back and continue. So we've done this. And then it says, complete the following table. Put an X if the number belongs to the set. You may put as many X's as you need. In the last column, name the best number system. So often on a test, that's what we'll ask you. So basically, it's the most specific, so the innermost number set on that diagram that best describes it. So remember natural numbers. So we're going to go through, I'm just going to put the notation here. So Z with a plus for IB. Whole is N. Integer is just Z. This is Q. This is Q the bar. Okay, so not a natural number, not a whole number, an integer. And so basically these three are involved in rationals. These are separate. So you're never going to put an X in both of these. So integer is part of rational. So the best description is the most specific. And this goes from most specific to least in terms of rationals. Irrational would be separate. So this will be integer. I'll just use the notation. Negative 16, very similar to negative 2. It's an integer. Rational, and so best description is integer. 9.2 is a terminating decimal, so it doesn't fit into the first three here. It's a rational, and so the best description is rational. 2/5, same as 9.2. It's a rational. Numerator and denominator are integers, so that fits in. Root 20. 20 is not a perfect square, so it does not simplify to a natural number, so it's irrational. So if you take a look back at the description here, best number system, it actually doesn't list irrational, so it says real number. So really, here we're going to put real number system. Okay, so these together add up to the real number system. The total of all the numbers in these two is the set of real numbers. But in this case, we're asking you if it's irrational, basically, to show it as a set of real numbers. Root 9 is 3, so that's a natural number, which is whole, which is an integer, which is rational, and so that's rational. Sorry. And most specific is natural. Okay, there we go. Pi is irrational, so we'll show that as real numbers. So kind of separate. We'll always have either the box for rational or irrational set out. Okay, 0 is not a natural, but it is a whole number, and integer and rational. So whole number is n. Negative 4 1/3. Just be careful on this. People see a negative and they think it's an integer, but it's got a fraction with it. So you know it's going to be rational right away. Then 28 is pretty basic number. It's a natural number, which is a whole, which is an integer, which is rational. So the most specific is natural. 0.121212. So we can show that is 0.12 repeating. And so that's a repeating decimal. Can't show it as an integer or a natural or a whole number. So it's a rational. 3.14, don't be tricked. It's not pi. There's no dots after, there's no other digits. So this is just a decimal, a terminating decimal. So this is terminating. So that's rational. Oops, there we go. And then this one, 4.2525552555. There's a pattern, but it's not a repeating pattern. So that's irrational. Oops, just need an X there. Okay, and so we'll put the real number system. Irrationals are part of the real number system. 4.83 repeating. So that is a repeating decimal, so that's rational. 16/7 is a fraction made up of integers, so that's rational. 48/6 is a fraction made up of integers, but it actually simplifies to 8. So that's a natural, whole, integer, rational. So that most specific is there. So really there is only how many irrationals? 3 irrationals. So you can, so really more specifically is Q with a bar. But in the directions for this question, they said they didn't list it, right? So that's why we put the real number system, okay? So that's that. Real numbers are whole numbers, but not all whole numbers are natural numbers. Name the only whole number that is not a natural number. Well, the only difference is that 0, okay? Because natural numbers start at 1. So set brackets 1, 2, 3, 4, and go onwards in that patterning. And whole numbers start at 0, 1, 2, 3. So all the same except for 0. Likewise, all whole numbers are integers, but not all integers are whole numbers. Name 3 integers that are not whole numbers. That would be negative. So let's say -1, -2, -3. So what type of integers are these? These are negative. Okay. In the following diagram, shade in the section that represents all integers that are not whole numbers. So remember, these are whole numbers. These are integers. Oops, didn't spell that right. Just give me a sec. Okay, so shade in the section that represents all integers that are not whole numbers. So that would be everything that's outside of the whole numbers. Okay. Name a rational number that is not an integer. What type of rational numbers are not part of the integers? So a rational number that's not an integer would be something like 2/3. What types of rational numbers are not part of integers? Well, they are fractions. I mean, they can be converted to decimals, but fractions that cannot be reduced to an integer. So basically, they don't have a common factor that can be reduced. So place the numbers in question 7 in the appropriate section in the diagram below. Okay, so that's all labeled. I'm just going to dual page so we can do this a little bit easier. Okay, so -2, that's just an integer, right? So if we take a look here, this will give us a hint to do it quickly. So -2, -16, 9.2, 2/5. Then root 20 would be over here. Then root 9 is in the middle. It's a natural number. Pi is irrational. 0 is a natural number. -4/3. 28. And 0.12. So 0.12 repeating. So that's, and we'll put that over here, 0.12, and I'll just use the repeating symbol. 3.14 is rational. Then irrational, 4.25255, 2555, etc. Then 4.83 repeating. Then 16/7. Then 48/6, remember that was equal to 8, and that was the best description was the natural number system. And so that goes into the middle. So 48/6. Okay, and that's the end of this lesson. Okay, so we'll stay tuned for the next.